Here we go. The problem with this one is you have a radical. You're going to have to rewrite that as 6x to the to the 1/2 power. Now, this is a problem that most of you had, or many of you at least. It has to be this entire quantity to the 1/2 power. Too many of you merely wrote it like this, like the 6 wasn't underneath the radical. The 6, of course, was underneath the radical, so all of that has to be to the 1/2 power. No matter how you work out this problem, you're going to have to deal with the derivative of what's inside, the dreaded chain rule here. Also, one of the things I did to make this easier was take this up to the top, where I'd had the quantity 6x to the negative 1/2 power times the natural log of 4x plus 3. Notice once again, they're going to have to use the product rule. And my advice would be to split it right there. And you've got an x times an x. So again, it'll be the derivative of the first times the second plus the derivative of the second times the first. All right, so the derivative of the first. You've got the quantity to the negative 1/2 power. Move the negative 1/2 down in front. Take 6x to the negative. You have to subtract 1, folks. That's like subtracting 2 over 2. Would give you negative 3 over 2. Now you have to remember to take times the derivative of what's inside. The derivative of 6x is a 6. So all of this is just the derivative of the first times the second plus the derivative of the second. Well, the derivative of the natural log of anything? 1 over anything. But again, you have to remember times the derivative of what's inside, folks. So all of this is just the derivative of the second times the first. Half credit for getting this far, and many of you, to your credit, did get this far, of course, but this was the hardest problem on the test because there's a lot to deal with here. You've got these negative fractional powers, and as you'll see in a minute, this radical will need to be reduced. So let's just start breaking it down. First of all, negative 1/2 times the 6, well, that's just negative 3. This moves to the bottom where it becomes 6x. That's a square root. And you're going to essentially take that to the 3rd power. Of course, this will be times the natural log of 4x plus 3. Treat it like it's that over 1. The denominator times 1 is just the denominator. And this ends up in the top. But you'll notice we've got something we have to play with here in the denominator. You've got this cubed, folks. This is the square root of 6x times the square root of 6x times the square root of 6x. The square root of 6x times the square root of 6x is simply just 6x. So 6x, and then I've got a radical 6x left over. Then in the numerator, I've got a negative 3 and a natural log of 4x plus 3. Well, you see what's going to happen here? Would leave you with a negative 2 in the denominator. So we have a negative, wherever you're going to put it, fraction. This will be the natural log of 4x plus 3 all over, whoops, I didn't really put it there, 2x radical 6x. I thought that was the hardest algebra on the test right there. Well, let's just fix this other one. It's fairly simple. 1 over that times 4, frankly, would simply be 4 over 4x plus 3. This needs to be moved to the denominator, where it would become a 6x to the positive 1/2 in the denominator, but that's simply then the square root of 6x. But you have to take it times the entire denominator, so times the 4x plus 3. And this was the way I expected to see the answer written. All right, the next one's not so bad. It's another product rule. Once again, unfortunately, you're going to have chain rule inside the chain rule. So let's kind of write our pattern down again. The derivative of the first times the second plus the derivative of the second times the first. When you do the derivative of the first and the derivative of the second, again, they're both chain rules. So the derivative of the first, that's e to the anything. The derivative, of course, is e to the anything. And then times the derivative of what's inside. It's not just an x, it's a 5x squared. The derivative of that, of course, is 10x. times the second, so that just stays 4x plus 8 to the fourth, plus the derivative of the second, move the 4 down in front. It's a simple power rule. Subtract 1 from the power, and again, times the derivative of what's inside. The derivative of 4x plus 8 is just 4. Times the second, so times e to the 5x squared. All right, now there's just some simple simplification to do here. I really prefer if you move this 10 and the x in front. This isn't even simplification, it's just reordering. If you didn't do it, I still give you full credit for it. That's the first term. Second term is just a little piece here to do. 4 times 4 is 16. We've got our e to the 5x squared, and then a 4x plus 8 cubed. And that's simply the way I expected to see 15 written. All right, now here are the two big problems on your test. I didn't do the directions very well. I reworded them in class, but again, I guess that was more on the second derivative test. But basically, you need to do the first derivative test for everything. It said run the requested derivative test to find the critical points. Okay? Now, you always use the first derivative to find the critical points. Again, I could have said that better, but I did re-say that in class. You must show both the first and second derivatives on both problems, but you have to use the first derivative test on this problem to determine whether they're maximums or minimums. All right, so basically, with that background for explanation, the first thing you needed to do was simply factor. And you guys did a great job at this. The basic stuff, you guys were solid on this test. So here's my derivative, my first derivative of the given function. You set that equal to 0 because we want to find where the tangent lines are horizontal or have a slope of 0. So here's where you guys had your problems. And once again, as always, it's an algebra problem. Many of you really struggled at this, frankly, very basic factoring problem. You need to be ready for this on the retest. I promise you, you're going to have to do some basic, not hard, factoring, but you're going to have to factor. The first term times the first term gives me my first. So the first times the first gives me the first. This has to be 3 times 1 and x times x to give me the x squared. Since this is a negative, one of these will have to be negative and one of these will have to be positive. Because again, my last times my last term gives me my last term. One of them's got to be positive, one of them's have to be negative. Probably, this doesn't always work, but probably the negative will be times the bigger term. So that's probably the negative. This is probably the positive. If that's not right, we'll just switch it at the end. The only possibility for -1, frankly, is 1 times 1. Set this equal to 0. And of course, if you check your inside and outside, this would be a positive 1x. The outside would be a negative 3x. And combine them, and you do get the appropriate middle term that we needed. So we have it factored properly. This times this equals 0. So either 3x plus 1 equals 0, or x minus 1 equals 0. Well, this one's easy. X equals 1. This isn't so bad either. 3x equals -1. Divide both sides by 3, and x equals -1/3. Let's do the same thing with the second derivative. The second derivative, we'll just take the derivative of our first derivative, of course. 3 times 2 is 6. X minus 2, again, equals 0. 6x equals 2. Divide both sides by 6, and we get 2/6, which of course reduces to 1/3. I think literally every single one of you that got this far did that appropriately. All right, so now we just have to determine what these critical points are, why, what's going on. First derivative test, here's what we do. I've got a critical point at -1/3, and I've got a critical point at +1. So we have region 1, region 2, and region 3. To figure out what's going on in region 1, frankly, I just need to plug in any value from region 1 into my first derivative. That's why they call it a first derivative test, folks. And I tended to go ahead and just plug in -1 because it was the easiest value. If we plug that into the first derivative, and you can plug it into either here or here, basically you have 3 times -1 squared minus 2 times -1 minus 1, which worked out to be a +4. Well, if the derivative is a positive 4, that means the slope of the tangent line at that point is 4. That means your curve must be going up, which means the curve in region 1 is increasing. So if I draw that on my diagram, it looks like this. Region 2, anytime, folks, you have the possibility of plugging a 0, do it. Plugging a 0 just cancels all the x terms and you're left with -1. So my first derivative, make the right symbol there, folks. First derivative at 0 is a -1. Well, obviously, if the tangent line at 0 is -1, that means the line is going down at that point, or decreasing in region 2. Region 3, I just got to pick a number in here. The easiest number for me was a 2, so I'll plug a 2 into the second derivative. And when I did that this time, I just got a +7, which once again means the curve is increasing. So what's going on here? Obviously, the curve increased and then it decreased, so this must be a local maximum. So I have a local maximum at -1/3. Over here, it was decreasing and then shot up, so I have a local minimum at +1. And finally, the inflection point. Don't forget that. The inflection point happens wherever the second derivative was equal to 0, and that happened at +1/3. So that's it for the first derivative test. Let's look at the second derivative test. I want you to do this basically the same way. Once again, and this one is actually much easier, and you guys did a much better job, but let me run through this quickly. If I take the first derivative of this bad boy right here, the first derivative would be 3x squared minus 6x. Set that equal to 0, and this is much easy factoring. I just had to take a 3 out of both terms and an x out of both terms, which left me with an x minus 2. So either 3 equals 0, because this is 3 times x minus 2. So either 3 equals 0, x equals 0, or x minus 2 equals 0. So either, that means really, because 3 can't be 0, either x has to equal 0, or x minus 2 has to equal 0, which means x equals 2. So they're my critical points at 0 and 2. Now, second derivative, because I'm going to need the second derivative to be able to run my second derivative test. Taking the second derivative of this makes it 6x minus 6, making that equal to 0. I take the 6, and I apologize for my grandson, but that's okay. We're not going to pause. We're going to keep going. Divide both sides by 6. The way the first test went, you probably heard a lot of crying in the background anyway, so you guys will be used to that, hopefully. It won't interfere too much. I've got a critical point at x equals 1. Now, this is up to you, folks, but I like just saying these in order. I've got something going on at 0, I've got something going on at 1, and I've got something going on at 2. This time, though, to determine what's going on at these critical points, I'm going to plug those values directly into the second derivative. So if I plug in a 0 into the second derivative, I have 6 times 0, which is 0, minus 6, of course, is minus 6. Then I'm going to plug in the 1 into my second derivative. But you know what, folks? I don't have to do that. I already know that the second derivative equals 0 at 1. But if you chose to plug it in, and you could, 6 times 1 is 6, minus 6 does indeed equal 0. And finally, plugging my 2 into my second derivative gave me 6 times 2 is 12, minus 6 is a positive 6. Remember telling you in class how often you saw this happen? It's pretty frequent on these very algebraic type equations that you have the same number, one positive, one negative. At any rate, let's analyze what's going on here. This says the second derivative at this point is negative. That means it's concave down, folks. So that would make that a maximum. Of course, where the second derivative is equal to 0, you have an inflection point. And I won't bother to spell the whole word out, just for time. And the last one, folks, the second derivative is positive, which means it's concave up, which means that's a minimum. And of course, I'm ignoring the local versus